In this video, we're going to talk about Taylor series, which is a way of taking a familiar function, such as sine, cosine, e to the x, or a rational function, and representing it as a series. There are a few advantages to this. One, and probably the most important one, is that if you have a series representation for a function, it becomes very easy to calculate its derivative and its antiderivative, because that can be done using the sum and the power rules, one term at a time. But we'll see some other uses for the Taylor series. We'll also see how it can be used to calculate the value of numerical series, and we'll see tomorrow how the Taylor series can be used to approximate the value of a function at a potentially pesky input value. So the goals for today: find the Taylor series representation of a function. Find in particular the Taylor series representations of a few canonical functions, 1 over 1 minus x, cosine, sine, and e to the x, and use those to find the Taylor series representation for other related functions. Then use those series to calculate the value of some numerical series. And finally, we have a special exercise for you in the concept check for today to prove what's called Euler's identity. Now, just a heads up, y'all, while you are listening to my voice, I want to make sure you know how to pronounce this person's name. This is pronounced Euler, not Euler. This is pronounced Euler. This person is Swiss. All right, let's get started. So in the previous video, we saw that this particular power series, which we dealt with in the exercises, turned out to exactly represent the function e to the x. And we deduced that by taking the derivative of the power series and noticing that the derivative of that series was equal to itself. The exponential function was the only function that was equal to its own derivative, and therefore the series had to be equal to the exponential function. But in cases where we're not necessarily that lucky, where the function that we're dealing with doesn't have such a unique property, how can we tell if a power series is equal to a function that we're already familiar with from another course, such as sine of x, for example? This brings us to the following theorem, a theorem that we can use to decide whether a power series centered at a number a is equal to a function that we might already have. Consider a power series, sum as n goes from 0 to infinity of some coefficient times x minus a to the power n. This is a power series centered at a. This series is equal to a function f of x if the nth coefficient of the series is always the same thing as what you would get if you took the nth derivative of the function, evaluated it at the center, and divided it by n factorial. If every single coefficient in your power series centered at a can be expressed using this formula, then the power series is equal to your function f of x. Not only can this be used to check whether a known series is equal to a known function, this can be used to find a power series representation for a known function, so that we can do things like take derivatives and integrals one term at a time. This particular power series representation for f of x the power series where we're summing as n goes from 0 to infinity the coefficient obtained from the nth derivative divided by n factorial times x minus a to the n. This power series is called the Taylor series for f of x centered at a. So let's practice obtaining the Taylor series for a function at a given center. For example, they say find the Taylor series centered at 0 for each of the following functions. And to begin with, we have the function e to the power x. So what we need to do when we find the Taylor series representation for a function is we need to figure out the formulas for the coefficients. C sub n, which is equal to the nth derivative evaluated at the center divided by n factorial. So let's go ahead and calculate the derivatives of the function f of x equals e to the x. Of course, e to the x, if you take the derivative, you just get e to the x. And the same thing if you take the second derivative and the third derivative and so on. If you take the derivative of e to the x, however many times, you're still just going to get e to the x. And so if I plug in the center, in this particular problem, if I plug in a equals 0, then the nth derivative, evaluated at 0, is going to be e to the power 0, is going to be 1. Therefore, what is the nth coefficient for the Taylor series for this function? The nth coefficient is equal to the nth derivative, 1, divided by n factorial. So let's put this all together in sigma notation to finish this problem. The function e to the x is equivalent to the Taylor series, sum from 0 to infinity, where the nth coefficient is equal to 1 over n factorial, and then multiply that by x minus the center to the power n, which can be simplified. The sum from 0 to infinity is simply x to the power n divided by n factorial. So this is the same result that we found implicitly yesterday. Yesterday we were given this series and we noted that it had to be equal to e to the x because that series was equivalent to its own derivative. In this case, we can use the Taylor series theorem as another way to make that same conclusion. The Taylor series for e to the x is the sum of x to the n divided by n factorial. Let's try it with cosine x. Cosine x, so once again, we need to figure out the formulas for the coefficients of the series, which amounts to figuring out a general pattern or formula for the derivative with 0 plugged in, 0 still being the center in this problem. So we have f of x, which is the same thing as no derivatives have been taken, and that's equal to cosine x. If we plug in the center to the 0th derivative, we get cosine of 0, which is 1. So let's look at f prime, which is the first derivative. If I take the derivative of cosine, I get minus sine. And if I plug 0 into sine, then I definitely get 0 as the result. Let's try it with the second derivative. The derivative of minus sine becomes minus cosine. And if I plug 0 into negative cosine, then the result is negative 1. Then the third derivative, the derivative of negative cos, is positive sine. And if I plug 0 into that, then 0 is the result. Notice something interesting about this function. As soon as we get to the fourth derivative, the derivative of sine is equal to cosine x, which means that we have essentially looped all the way back around to what we started with. We have the fourth derivative is equal to the 0th derivative, and therefore the fifth derivative must be equal to the first. The sixth must be equal to the second, and so on. We've entered a loop. So let's write out a couple of terms in this series, and let's see if we can express a general formula in sigma notation for this Taylor series for cosine. So the first term in the sequence is going to be equal to the 0th derivative divided by 0 factorial times x minus 0 to the power 0. The next term is going to be the first derivative divided by 1 factorial x minus the center to the power 1. Then the second derivative divided by 2 factorial x minus the center to the power 2. Then the third derivative, 3 factorial x to the power 3, and so on. After that, the derivatives are just going to keep repeating in value. So it's going to loop back and become 1, 0, minus 1, 0. 1, 0, minus 1, 0. That pattern of derivatives is going to continue on toward infinity. So because of that, all of the odd powers of x are going to vanish. Because of that 0 in the front, it will cancel out this term. All the odd powers will vanish and only the even powers will be left. So we'll have 1 over 0 factorial x to the 0th power minus 1 over 2 factorial x to the 2nd power, and then plus 1 4 factorial x to the 4th power minus 1 6 factorial x to the 6th power, and so on and so forth. So when you see this series represented in sigma notation, this is how you're generally going to see it. The sum, as k goes from 0 to infinity, x to the power 2 times k. X to the power 2 times k, so that only the even powers will show up. When k is 0, we get a power of 0. When k is 1, we get a power of 2. When k is 2, we get a 4. When k is 3, we get a 6. We'll also use this in the denominator. The denominator, we have the factorial of even numbers only. 0 factorial, 2 factorial, 4, 6. So we will do 2k factorial to ensure that that number is always even. Finally, to capture the fact that this series is alternating plus minus plus minus, we'll include a negative 1 to the power k. And this is the sigma notation for the Taylor series centered at 0 of the function cosine x. Let's also try it with sine of x. Sine of x, we have the 0th derivative is equal to sine. And if I plug the center into that function, I get sine of 0, which is 0. The first derivative is cosine. And if I plug in the center into the first derivative, I get cosine of 0, which is 1. The second derivative is now the derivative of cosine, which is negative sine. And if I plug the center into negative sine, I get 0 again. Then the third derivative is negative cos. And if I evaluate the third derivative at 0, I get negative 1. Now sine, just like cosine, has a looping behavior. As soon as you go to take the fourth derivative, you're going to get back positive sine. And then once the fourth derivative is equal to the original function, the fifth derivative must be equal to the first, the second must be equal to the sixth, and so on and so forth to infinity. So, sine of x is equal to the series that we get by taking the 0th derivative, dividing it by 0 factorial, times x minus the center to the power 0. Then the first derivative divided by 1 factorial, x to the power 1. Then the second derivative divided by 2 factorial, x squared. Third derivative, third factorial, third power, and so on and so forth. Now, in the series for cosine, all of the odd powers ended up vanishing because the odd powers were in contact with the number 0. But for sine, all of the even powers ended up vanishing because x to the 0 is in contact with 0, x squared is in contact with 0, and so will be x to the 4th power, x to the 6th power, and so on. So sine x, an odd function, only has odd powers of x in the series. So how do we use sigma notation to capture the fact that we only have odd terms in this series? We can do the following. We're still going to sum as k goes from 0 to infinity. But instead of using x to the power 2k, we're going to write x to the power 2k plus 1. That way when k is 0, we get an exponent of 1. When k is 1, we get the 3. When k is 2, we get the 5, so on and so forth. Likewise, to capture the fact that the number in the factorial is also always odd, we're going to write 2k plus 1 factorial. And then, as usual, to capture the alternation, we're going to use a negative 1 to the power k. This is the power series centered at 0, representing sine of x. These two quantities are equal for any value of x that you want to plug in. As our last example, we have 1 over 1 minus x. Now, we can use the Taylor series formula to represent this as a power series, but I want to show you another principle, another trick that applies specifically right here. Let's recall that the geometric series formula gave that the sum from n equals 0 to infinity of x to the n was equal to 1 over 1 minus x. In any case where the series on the left actually converged, the value of that series was equal to this quantity on the right. Now, up to this point, we used that formula in the forward direction to rewrite this series as a function. But it holds just as true in the reverse direction. To say if we want to take this 1 over 1 minus x and rewrite it as a series, then we can use this formula backward. It's the same thing as x to the n. Now these four formulas that we have obtained, the power series representation for 1 over 1 minus x, the power series representation for sine, and the power series representation for cosine and exponential function, these are quintessential formulas that I really think that anyone who is interested in becoming a math major should definitely memorize and know by heart. Now, if you are going into physics, if you are going into electrical engineering or something like that, you have your own set of formulas that need to be memorized to succeed in your field. But if you're planning to be a math major, these four series should be sewn into your heart. They should be internalized and memorized. Let's do one additional example of finding a Taylor series in the case where the center is something other than 0. Let's find the Taylor series representation for the natural log of x centered at x equals 1. Now, the first thing that I would like to make a note of is why this Taylor series is not centered at 0. And the simple reason is that in order to construct the Taylor series representation for a function, the very first thing that you need to do is you need to plug the center into the function. But the natural log of 0 is not actually defined. And in addition to that, neither are any of its derivatives. In order to center a Taylor series at a number, we need to make sure that every single possible derivative is defined at that center value a. Alright, so the 0th derivative, the original function, is undefined at 0, which means centering the function at x equals 0 is not appropriate. So instead, we're going to choose the next simplest number, which is x equals positive 1. Alright, as usual, let's start by calculating the derivatives of the function. The 0th derivative, the original function, is the natural log. And if I plug the center into that, if I plug 1 in this case into that function, I get the natural log of 1, which is equal to 0. Then the first derivative, which is 1 over x. And if I plug 1 into that, then I get 1 over 1, which is equal to positive 1. Then, using power rule, the second derivative is negative 1 over x squared. So plugging 1 into that, we get negative 1. So our first derivative, positive 1, gets multiplied by x minus 1 to the first power, x minus the center to the first power. Then our second derivative has minus 1, we divide it by 2 factorial, and we get x minus the center to the second power. So in sigma notation, what pattern are we observing? First of all, we're summing up powers of x minus 1, starting from the first power at 1. The next thing that I notice about this pattern is that the terms are alternating in sign, starting out with positive, then negative, then positive, then negative, then positive. So my inclination is to put a negative 1 to the k here in front. However, this is currently not quite correct, because when k is equal to 1, negative 1 to the first power will output a negative value. However, my k equals 1 term outputs a positive value. So what I'm going to do is I'm going to take that negative 1 to the k, and then I'm going to add 1 to this exponent. Let's confirm that when k is equal to 1, the exponent k plus 1 becomes 2. So I have minus 1 to the power 2, which outputs a positive value. So I had to make a slight modification to the power on negative 1 in order to make it alternating but alternating in the correct way, starting with positive and then becoming negative. Now the next thing and the last thing that I'm going to observe about this series is that we have denominators which are always a match to the power on the x minus 1. So if the exponent is k, then the denominator is also going to be k. And this is the sigma notation for the Taylor series centered at x equals 1 for the function natural log of x. Now once you have the Taylor series of a couple of functions, you can use those series to find representations for other functions without having to go through this tedious process of calculating all these derivatives and plugging the center into the derivatives. There are a few different techniques that can be used to take one Taylor series and obtain another. For example, one technique is the technique of substitution. To show you what I mean, someone says, find the Taylor series centered at 0 for the function 1 over 1 plus x squared. Now I'm going to notice how similar this is to the function 1 over 1 minus x, which we found was equal to the sum as n goes from 0 to infinity of x to the n. I'm going to notice the fact that this function is almost exactly the same, except instead of having an x subtracted from 1 in the denominator, we have a negative x squared subtracted from 1 in the denominator. Negative x squared replaced the variable x. So I'm going to do exactly the same substitution in the series on the right. Instead of raising x to the power n, I'm going to raise the substituted quantity negative x squared to the power n. Now if you like, you can rewrite this a little bit and use some properties of exponents to turn this into negative 1 to the n, x to the 2n. This series is the Taylor series representation for the function 1 over 1 plus x squared. It has the correct format, x by itself to a power with a coefficient in front. You can also do some arithmetic to find your way from one series to another. For example, let's find the Taylor series centered at 0 for the function x divided by 1 plus x. In this case, how is this function related to our friend 1 over 1 minus x? Our function is equal to x times 1 over 1 minus negative x. Factoring out the x in the numerator and thinking of the denominator not as 1 plus something, but as 1 minus something. Now the quantity in the parenthesis can be written as the sum as n goes from 0 to infinity, not of x to the power n, but now we know that this is equal to negative x to the power n, substituting negative x in the x's position. So let's rewrite that ever so slightly. This is the sum as n goes from 0 to infinity, negative 1 to the n times x to the n. Now what happens if we multiply that by an extra factor of x? Then anywhere there was an x to the n, there is now an extra x, so I get x to the power n plus 1. This series is equal to the function x divided by 1 plus x. We found that not by calculating any derivatives or using the Taylor series formula, but by taking a known series, first of all doing a substitution, and then multiplying through by the extra x that we had. You can also find Taylor series by taking the derivative of a function. For example, we want to find the Taylor series centered at 0 of the function 1 divided by 1 minus x squared. And I'm going to note the fact that 1 over 1 minus x squared is equal to the derivative with respect to x of 1 over 1 minus x. This comes from either the quotient rule or the chain rule. What this means is, if I wanted to find a series for 1 over 1 minus x squared, I can do this by taking the derivative of the series for 1 over 1 minus x. So just using power rule here, the series for 1 over 1 minus x quantity squared can be found by summing from 0 to infinity the quantity that we get by multiplying by n x to the power n minus 1 as just a result of sum and power rule. Finally, potentially the most complicated example, we can also get Taylor series from functions by integrating series that we have already obtained. So for example, they want us to find the Taylor series centered at 0 of the function arctan of x. Now the neat thing about arctan is that this is an antiderivative of the function 1 over 1 plus x squared. We have already found that 1 over 1 plus x squared could be obtained by summing from 0 to infinity the quantity negative 1 to the nth power times x to the 2n power. So let's integrate both sides with respect to x. The left side works out to be arctan x. The right side works out to be negative 1 to the n, then increase the power, divide by the increased power from 0 to infinity. Now pause for just a second. What is missing from this equation? What have I not included that was oh so important anytime we calculated an antiderivative in Calculus 2? Of course, what's missing is our plus c. The plus c, which is the unknown added constant which we have to account for anytime we take an antiderivative. What would c have to be in order to make the quantity on the right side actually equal to arctan of x? To determine the value of c, let's plug in the center. X equals 0. Let's plug the center in for x and let's see what happens. On the left side we have arctan of x. But now x is 0, so let's consider arctan of 0. Then we have the sum as n goes from 0 to infinity, negative 1 to the n times 0 to the power 2n plus 1 divided by 2n plus 1. Now arctan of 0 is equal to 0. And because 0 to any positive power is equal to 0, all these terms in the series vanish, and I'm left with 0 equals c. So having determined that, I can safely conclude that arctan of x is equal to the sum as n goes from 0 to infinity, minus 1 to the n, x to the 2n plus 1 power divided by 2n plus 1, plus 0. There is no constant term necessary to make the right-hand quantity equal to the left-hand quantity. To give you an idea of one of the useful applications of power series, let's consider the infamous e to the x squared. I say infamous because the antiderivative of e to the x squared cannot be found cannot be expressed using any of the functions that we have studied up to this point. The antiderivative of e to the x squared cannot be expressed as any combination of polynomial, rational, trigonometric, exponential, or logarithmic functions, or radical functions. However, we can use power series as a representation for the antiderivative of e to the x squared. In order to do that, we're first going to need a power series representation for e to the x squared itself. So I'm going to note that e to the x squared is basically the same thing as e to the x with x replaced by x squared. Now we already know the power series representation for e to the x. And if you're a math major, or if you're intending to be a math major, you should certainly have this memorized. Now this is equal to x to the power n divided by n factorial, summed from 0 to infinity. So if I go in and substitute x squared in x's place, then that same thing will occur in the series. And I will get x squared to the power n divided by n factorial, or if you prefer to have that simplified a little bit, x to the 2n divided by n factorial, summed from 0 to infinity. So let's go ahead and let's use that to find a power series representation for the function f of x, in other words, one of the antiderivatives of e to the x squared. So what I'm going to do is I'm going to say this function, which is equal to the integral from 0 to x of e to the t squared dt, can be found by taking the integral from 0 to x of this power series. So what I'm going to do is I'm going to take the integral one term at a time using the power rule. So t to the 2n plus 1, increasing the power by 1 unit, and then divide by that increased power. Evaluate this as t goes from 0 to x. Now as before, if I take 0 and raise it to any positive power, then 0 to a positive power is just going to vanish. So all that's left is the sum, as n goes from 0 to infinity, of x to the power 2n plus 1 divided by n factorial times 2n plus 1. And this is a power series representation for the function which is the antiderivative of e to the x squared. Now one of the major benefits of having a Taylor series is that it can be used to calculate the exact value of some convergent series that we encountered in previous sections. For example, we have this alternating series, sum as k goes from 1 to infinity, negative 1 to the power k divided by k. And we want to show that this is equal to the natural log of 2. So what I'm going to do is I'm going to start with the sum as n goes from 0 to infinity of x to the n is equal to 1 over 1 minus x. What I'm going to do is I'm going to take the antiderivative of both sides. I'm going to try and take the antiderivative to try and obtain a quantity that has the natural log in it. So if I integrate the left side, I have the sum as n goes from 0 to infinity, x to the n plus 1, divided by n plus 1 by power rule. And on the right side, I have the natural log of the absolute value of 1 minus x with a negative sign in front of it. Having found the antiderivative of both sides, let's add plus c, and let's determine what value does c have to be in order for both of these quantities to be exactly equal. So let's plug in the center. Let's plug in x equals 0 to both sides, and let's see what happens. On the left-hand side, we have c plus the sum from 0 to infinity, 0n plus 1 over n plus 1, which is equal to natural log of 1 minus 0. Now 0 to a positive power always vanishes. And then we're left with c equals the negative natural log of 1. Natural log of 1 is equal to 0. Okay, so c is equal to 0. So what we have found is that the sum, as n goes from 0 to infinity, of x to the n plus 1 divided by n plus 1 is equal to the negative natural log of the absolute value of 1 minus x. But let's find out a couple of terms of this series on the left side, and let's see if we can rewrite it in a way so that it more closely resembles the series that we're given in our problem. When n is equal to 0, this quantity is equal to x to the first power divided by 1. Then when n is equal to 1, we get x squared over 2. When n is 3, x3 over 3, and so on. But notice that this series on the left can just as well be written as the sum starting from 1 to infinity of x to, let's call it k. If k is equal to 1, we get x to the first power over 1. If k is 2, we get x to the second power over 2. If k is 3, we get x cubed over 3, and so on and so forth. Now, we have made sure that our series is in exactly the same format as the series that we were given in the equation that we're trying to prove. The only difference now is that the series that we were given has a negative 1 to the k instead of our series, which has an x to the k. So let's plug in x equals negative 1. On the left-hand side, we now have the sum from 1 to infinity, negative 1 to the k, divided by k. Plug it in on the right side, and we have the absolute value of 1 minus negative 1, which is 2. And with that, we have proved that this formula is true. With that, we have calculated the value of this series. That is a specific case of the general formula that the sum as k goes from 1 to infinity, x to the k over k, is equal to the negative natural log of 1 minus x. This same formula could be used to find the value of all kinds of different series as long as they fit into this general format. To summarize what we did today, we talked about the Taylor series representation for a function. We gave the formula for the Taylor series representation in terms of the derivative, and we practiced using that formula to find the series representing e to the x, cosine, sine of x, and 1 over 1 minus x. Then we introduced some alternate ways to find Taylor series by applying some calculus and algebra techniques to the series that we had already obtained for some given function. Finally, we used Taylor series to find the exact value of some convergent series from previous sections, such as our friend negative 1 to the power k divided by k.